So today we will discuss first about electric dipole and we will derive equations for the field strength due to a dipole at a point on the axial line and at a point on the equatorial line. So then we will go for the electric flux, and then we will continue with Gauss laws, because that the flux is related to Gauss laws. So that topic I will tell you later. So let us continue our this electric dipole concept. So what is an electric dipole? It is nothing but two equal and opposite charges. Say suppose they are separated by some distance. Then this is called as a electric dipole. A dipole has a direction. By convention, the direction is taken from minus q to plus q. So this is the direction of the electric dipole. The distance from the center of the dipole to either of the charges is taken as, say, some a in this case. Now, the net charge of a dipole is 0, but the electric field due to a dipole at a point need not be 0. But at far away points, when compared to the distance between the charges, if the point is far away from this center of the dipole, in such case the electric field strength becomes nearly 0, but not at the distances which are comparable with the separation between the charges. Therefore, let us derive expressions for electric field strength due to a dipole on the axial line and then on the equatorial line. So let us derive electric field strength. Electric field on the axial line. So here axial line means the line joining the center of the charges. So therefore, let us take a point. This is the dipole. So this is plus q, this is minus q. Suppose this is the center, and now extend this line joining the axis like this. Consider a point here, say some a. Now, to know the electric field strength due to a charge, we must keep a test charge here. The test charge is nothing but unit positive charge. So, due to this plus q, this test charge will experience a repulsive force. So let us say this is the repulsive force due to the charge plus q, and due to this charge minus q, it will experience an attractive force. But since that charge is far away from here, this vector is shorter than this vector. So therefore this will be minus f. They are not equal, so we will put some, this is f1, say some f2. So now the force experienced by the unit charge, and that we are calling it as force acting on unit charge, is treated as the electric field strength. Therefore, instead of writing the actual force, we will write something like E1, and this is something like E2. So since the vectors are lying on the same line, their sum will give the resultant electric field strength. So therefore, I can write like this: the force due to the electric field strength due to the positive charge, that is given by 1 by 4 pi epsilon naught, and here this is q by plus q can put. So by the square of the distance. See, let us take this separation. Here it is 2a, but from the center to this point, let us take the distance as r. So from the center to this point, I have taken the distance r, and therefore from the center, so this is the separation here. This is 2a. From this center to this point, the distance is taken as r. Therefore, due to this positive charge, I can write the electric field strength like this. So that is R. Therefore, E1 can be written as 1 by 4 pi epsilon naught plus Q by the distance from the center will be R minus here. So from the center, from here we have to calculate this distance. So this is R minus A. Therefore, here we have to write R minus A square. And similarly, from this point, the distance of this will be R plus A. Therefore, this point is at a distance of R plus A from minus Q. Hence, the electric field E2 due to this negative charge is written as 1 by 4 pi epsilon naught. This minus Q by R plus A whole square. Therefore, the resultant electric field is E1 bar plus E2 bar. But we can write it like this: 1 by 4 pi epsilon naught is common, and the Q is also common. Then what we get is 1 by R minus A whole square minus 1 by R plus A square. So just you simplify this. So when you simplify, what you get is that is equal to Q by 4 pi epsilon naught into, in the denominator you are going to get R square minus A square whole square, and in the numerator, so 4 RA will remain, the other terms get cancelled. So what you get in the numerator is 4 RA. The other terms gets cancelled, you can do it. So you know how to solve that, then you will get that 4A, 4 times RA. So this can be written as like this: 1 by 4 pi epsilon naught. I will be writing it in the brackets 2 into 2 Q into 2A into R by R square minus A square whole square. So why I am writing like this means, this has a meaning that the product of charge and separation between the charges in case of a dipole is known as dipole moment. And here you have to mention the direction also when you express that in the form of a vector. So that is, if you observe that here the force on the force on this positive charge, here it is more due to this plus Q. Hence that is E1 is greater than E2, because this field due to the minus Q will be, or the force on test charge will be opposite to this. Therefore, the resultant force will be in this direction, that is in the direction of the dipole, because you know the dipole direction is from minus Q to plus Q, as I said earlier, like this. So we can write like this: E bar can be written as 1 by 4 pi epsilon naught 2 times P by R square minus A square whole square. You put a vector, unit vector P bar, that is P cap, in the direction of the electric dipole. That is, the resultant electric field at a point on the actual line of a dipole is in the direction of the dipole. So it is along the axis and in the direction of the dipole, and this is the formula. But here you should know that this product is written as P, that is called as dipole moment. Now we consider a point which is far away from A, that is R is far greater than A. So let us take that point approximation and see how the formula changes. In such case, when R is far greater than A, you can drop this A here, A square. Then it will be R to the power of 4, and of course 1 R is ditched. So here we have R also. So this will be R power 4. So that 1 R gets gets cancelled, in the denominator we will get r cube. So therefore, E bar will be 1 by 4 pi epsilon naught 2p by r cube. So this will be the formula in the case of a point on the axial line which is far away from the center, or the distance is far greater than the separation between the charges of the dipole. So you observe that electric field strength is varying inversely with r cube, but whereas in the case of a single charge it varies with 1 by r square. That means the field strength decreases at a greater rate due to a dipole than due to a single charge. So now we will discuss the electric field due to a dipole on the equatorial line. So equatorial line means the perpendicular passing through the center of the dipole. So let us take this is plus q and this is minus q. Now this is the center. Now you can take this is the equatorial line. So let us consider a point here, say suppose A. Now to know the field strength, what we do is we keep a unit test charge there. So suppose this is the distance of the point from the center of the dipole. So if you keep a unit positive charge there, this charge will be repelling. So therefore the field due to this plus charge will be acting like this, and field due to this minus q will be acting like this. Of course they are equal, but their directions are different because the distance of this point from the center of the dipole is same. Therefore this field strength due to plus q and minus q at A is same, but the directions are different. Now by vector addition or by using parallelogram law, the resultant direction will be given by this. So you can complete this parallelogram and you can easily find that this is the resultant electric field strength. Suppose if this is theta, definitely you can find that this is theta. Now this is r, you know this length is a and this length is also a. So this is r, this is a. Therefore this is hypotenuse. So that must be equal to root of r square plus a square. Now from this you can write cos theta, because what we want is the component of electric field. You observe here. So this electric field can resolve into two components. One E cos theta in this direction and another is E sin theta. Similarly, this electric field can also be resolved into components. So one is along this, the other is along this. So that is E cos theta along this, and here you will have E sin theta. Therefore, these two equal and opposite they cancel. Only the E cos theta components will add up. So therefore, the resultant electric field is given by 2E cos theta. So that is what we can understand from the figure. So therefore, I can write what is this E? That is resultant E is equal to 2E cos theta. Now this is therefore here the dipole direction is like this, P cap. You observe this, but the resultant electric field strength is in the opposite direction to the dipole. Therefore, if you want to write this E resultant bar, then we must write 2E cos theta with negative sign into P cap. So why I am writing like this? Because the dipole direction is from minus q to plus q. But you observe the resultant electric field direction, it is in the opposite direction. That's why I wrote the symbol minus sign here. And you can easily understand that the cos theta from the figure, cos theta is what? So this is the adjacent side by hypotenuse. So that is r square plus a square under root. So therefore I can write like this, minus 2 into 1 by 4 pi epsilon naught and into q by. So that is the distance either from this side or from this side is same. So the distance square you have to write. So therefore square root of r square plus a square. So square of this into cos theta. Cos theta means a by root of r square plus a square into p cap. So that is what the resultant equation. So here I can rewrite it like this. This is minus 1 by 4 pi epsilon naught q into 2a by. So when you multiply these two, what you get is r square plus a square to the power of 3 by 2 into p cap. Okay. So this q into 2a, as I already told you, is dipole moment. Hence, therefore, the resultant electric field is given by minus, this is P by 4 pi epsilon naught r square plus a square to the power of 3 by 2 into some p cap. So, in the place of q into 2a, I have written the dipole moment, and this is the unit vector in the direction of the dipole along the axis, 4 pi epsilon naught in the denominator, r square plus a square to the power of 3 by 2. And suppose if r is far greater than a, as I said earlier, so let us take a point far away from the center of the dipole. In that case, you drop it. Again, what you get is E is equal to minus 1 by 4 pi epsilon naught P by R cube into the unit vector. So, this is the approximate formula for a point far away from the center of the dipole. So, here you see the direction of the electric field is opposite to the dipole direction, whereas along the axial line it is in the direction of the dipole. Here it is opposite to the direction of the dipole. So like this we can derive equations for the electric field strengths due to a dipole on the axial line and the equatorial line. Now we will consider what happens to the dipole if it is kept in a uniform electric field. So, and what happens in case of a non-uniform electric field. So, we will discuss this, that is electric dipole. In an electric field. So, let us consider a dipole is kept in a uniform electric field at an angle. So, let us suppose and say this is minus q, this is plus q, this is a dipole. You know the separation is 2a. Suppose this is the direction of the electric field. See, the electric field direction means, actually you will understand when you study about electric potential. If the electric field direction will be the direction along which the electric potential decreases at maximum rate. This you will study in the next chapter actually. So, while explaining you about electric field lines, I told you that the electric field lines give a pictorial idea about the electric field strength and its direction. In the case of a point positive charge, the electric field lines are drawn radially outward because the potential decreases in that direction at the maximum rate. That's why we draw the vectors in the direction outwards from the point positive charge. Similarly, in the case of point negative charge, you approach the charge along the radius. Considering that point charge at the center of a circle, then that will be the direction along which the potential decreases at maximum rate. So, in the case of a positive charge, as we move away radially, field decreases. And in the case of a negative charge, point negative charge, if you approach, the field decreases in the radial inward direction. So, generally whenever we represent a field, it means actually from higher potential to lower potential, the direction is shown. So that will be the decreasing direction of the electric field strength and of course electric potential also. So in that way we draw the electric field lines. So we call that is the direction of the electric field. So from a positive charge, as we move away, so what happens? The field strength decreases inversely as the square of the distance. And whereas in the case of negative charge, we say that as we approach the charge, field decreases. Okay. Now, what we study here is what happens to a dipole if it is kept in a uniform electric field. So, another point regarding this electric field is when the field is uniform, all the electric field lines are drawn parallel. In the case of a non-uniform field, these are curved. So, here let us imagine all the field lines are parallel, and I have shown one such arrow showing the direction of the electric field. Now, the dipole is at an angle. So, this is the angle made by the dipole axis with the direction of the electric field. Now, a force acts on minus q charge like this. So, this is the force on this. And similarly, a force on positive charge acts in the direction of the electric field. So, that is plus EQ. So, since the forces are equal and opposite, the net force on the dipole must be 0. But the effect of forces is not 0. Because you know that when two anti-parallel forces act on a body at different points, the effect is rotation. So, why they rotate means they rotate due to a torque produced by such pair of forces. So, we call them as couple. So, due to the couple acting because of these electrical forces, the dipole rotates. It tries to align in the direction of the electric field. So that is the effect. Now, how to calculate this torque? You know, the moment of the couple is given by the force multiplied with the perpendicular distance between the lines of action of the forces. So the lines of action means, so you consider this and this is. So this distance is what you are supposed to know. That is the distance between the lines of action of the pair of forces. From the figure, you know, if this is theta, this is 90 minus theta, because this angle is 90, hence this is 90 minus theta. And you know, this distance is 2a, that is the length of the dipole. Therefore, this distance will be 2a sin theta. If theta is the angle made by the dipole with the axis, that is with the electric field. So the axis of the dipole makes an angle, theta is the electric field direction. Then this will be 2a sin theta. And you know, the dipole moment R will be in this direction. That is the unit vector showing the direction of the dipole, P cap. Now, therefore, this is EQ into what is the perpendicular distance? 2a sin theta. So this can be written as E into 2a into Q. We can write it as dipole moment. So we can write it like a dipole moment. Therefore, in vector form, tau bar can be written as P bar cross E bar. That is P bar cross E bar. So you know how to use right hand thumb rule. Therefore, if you curl your right hand fingers like this, the torque will be along the outward drawn normal to this board. If you are using a paper, it will be out of the plane of the paper. So that is the direction of the torque acting on the dipole. So the dipole will try to align itself in the direction of the electric field. This is in the case of uniform electric field. In non-uniform electric field, what happens? Non-uniform. So this is uniform electric field. This is uniform electric field. And in non-uniform electric field, suppose say this is minus Q and this is plus Q dipole. And suppose this is the increasing direction of the electric field. So let us suppose this is the increasing direction of the electric field. Then what happens? The force on this plus Q will be in the direction of increasing electric field. On this it will be like this. So here increasing direction. So therefore, since the force on this is in increasing direction on plus Q, this is the direction of minus Q. Here this force is greater than this. The reason is the field here is more than the field here. Increasing direction is like this. Therefore, the resultant force will be in this direction. F resultant. So, in the case of a non-uniform electric field, the resultant force is not zero. It will experience a resultant force, and in this case, the resultant force will be the increasing direction of the electric field, and this is the dipole direction. In addition to this, in a non-uniform electric field, there is a possibility of rotation of the dipole. The dipole rotates and also translates in a non-uniform electric field. So here I have shown you like this. In this particular case, there will be a force in the direction of increasing electric field. So here the couple action is not shown. So simply we are saying it is a non-uniform electric field and it will experience a resultant force. Okay, if the field is increasing in this direction. Suppose if the dipole is kept like this, so the field is increasing like this, but dipole is reversed. So here we have minus Q charge, here we have plus Q. So the dipole direction has reversed. Then what happens? So on this, the force is like this, F minus Q, and on this the force is like this, plus Q. So the resultant force will be like this, F resultant. So the resultant force in this case will be opposite to the direction of the increasing electric field. That means in the decreasing direction. The resultant force on the dipole in such case will be in the decreasing direction of the electric field. So this is how we can explain the effect of electric field on a dipole. So if you keep the dipole in the uniform electric field such that the dipole makes some angle, then a torque acts, and as a result the dipole rotates. So it will not translate because the forces are equal and opposite, they cancel each other. But the effect of force is not zero. It turns the dipole. Whereas in case of a non-uniform field, there is a possibility of rotation and translation. But I have given here one example in which the field is increasing in this given direction. if the position of the dipole is like this, it will experience a resultant force in the direction of the increasing field. If the dipole position is reversed, it will experience a resultant force in the decreasing direction of electric field.